Astrogeodetic boundary value problem. So we all know that if it is, we have the geoid, and we have the ellipsoid. This one is geoid, and we have ellipsoid, and we have the train here, train. And if we plot a normal to the ellipsoid from the train, normal to the ellipsoid, and normal to the geoid, they are not coincident. They are not coincident. It means that we will have an angle here which is called deflection of vertical. Vertical. This deflection of vertical can be measured at the surface of the train, which is called surface deflection of vertical, or it can be counted here, which is called geoidal deflection of vertical. So here we assume that we have the geoidal deflection of vertical. So what is the geoidal deflection of vertical? If I draw a surface parallel to the ellipsoid, as we see that this is theta, again equal to this theta, the surface, the geoidal deflection of vertical. So deflection of vertical is, let me write theta. Theta is slope of geoid. So how do we measure it? Using astronomical data. We go and measure astronomical latitude, and we have geodetic latitude at the surface. Then we can compute the northeast component of that. And we can also compute it from the astronomical longitude and astronomical tangent. So we can compute the deflection of vertical simply. We can measure the deflection of vertical simply from using Laplace point. It's called Laplace points. Laplace points are points that they have astronomical coordinates and geodetic coordinates. So for example, at a point, we have astronomical coordinate, and how do we do it? With measurements to the stars. We will determine phi and lambda. That's called astronomical. But for the same point, we compute the geodetic latitude and geodetic longitude using the classical geodetic method, or ellipsoid's geometry. That's called geodetic. The difference between these two is that one quantity is geodetic, is pure mathematical, and the astronomical coordinates are pure physical, because they are very much affected by the gravity field, and so astronomical coordinates inherently has the gravity inside. They are affected by the inside. It's like geoid height that you can measure. Geoid height that you can measure by altimetry. You can measure the astronomical, or the component of the deflection of vertical from the astronomical measurements. So one side of this data is like geoid, is ellipsoid, and the other side is the real Earth, which is astronomical. So similar to the geoid. So that's after this short review. But the question is, how can we determine the geoid or gravity order from the deflection of vertical? So let me explain it in another way as well. Deflection of vertical is also, if you plot this theta here, theta is the angle, deflection of vertical angle. If we project it on the meridians, it will be psi, north south component, and we go here, and then it will be theta. So what is the relation between this? If we have the geoid height, eta is just slope, Kc is slope of the geoid. So what does it mean? It means the derivative of n, the geoid, with respect to theta. Or eta is derivative of n with respect to delta, lambda. So these are the measurements here. Is that the component of the gravity astronomical data are all measurements, and from this astronomical data, our goal is to determine, let me write it here, Kc and eta. The goal is to come to the geoid height, gravity anomaly, or gravity disturbance. But the question is how. So let me start with one of them. I will start with Kc, which is simpler. Kc is the derivative of the geoid with respect to theta. So I already have the derivative of the spherical harmonics of the geoid. If I take the derivative of that, I come to this formula. Kc is summation minus n to n, m, here derivative with respect to theta. So you have the spherical harmonics of the geoid here. And for eta, simply you can write again sine theta delta, then eta will be similar. Spherical harmonics, of the geoid, the derivative of a spherical harmonics with respect to lambda. So the question is now, if I have this theta and lambda, yeah, I have the Kc and eta. How can I come to the geoid, and how can I go to the gravity anomaly or gravity disturbance? That's the whole issue. If you want to derive the similar equation for Kc and eta in terms of the gravity disturbance and gravity anomaly, simply you can replace an m by, for example, an MBA already we know that magnitude was r over n minus 1 delta g n m, or r m plus 1 gravity disturbance. So if you wanted to have a relation, spherical harmonic relation between the astrogeodetic measurements and the harmonics of the gravity disturbance and gravity anomaly, simply insert them back inside the formula. You will get them. But That's not the thing that actually we want. The spherical harmonics, we need the data with global coverage, and we do not have actually, if you do astrogeodetic measurement, they are sparse. We do not have them everywhere in some place. Then we have to find another way for determining geoid, geoid or the gravity. So now let us do a little bit mathematical algebra to some algebraic manipulations to determine the gravity, the geoid. So if my goal is to determine an m, but the problem is here. Let me do it in that way. I rewrite it this psi in spherical harmonics form, and we write and then C and M y and m theta lambda. She should be first short from 2, sorry, 2. And m n y and m theta and lambda. So if I write it in that way, you can see that I cannot directly write that this term is equal to this, so I can separate the spherical harmonics simply. Then let me multiply y and m. Let me write it with another color. I will multiply. I've tried to write it smaller. And the m, y and m, theta lambda. I multiply, for example, y and m, theta prime, lambda prime. Here, and I take the average, the integral, both sides, the sigma equals to, then I will write again the other formula, 2 from, so nm, derivative of nm, that is theta lambda, multiplied by, now I write it by red so that you can see the difference, theta prime, lambda prime, this. So, we have already seen that, if we multiply these two, we have the integral, the result will be 4 pi delta n. However, this is not the case. This is not the case for here. Even so I forgot this integral behind this. So this is not the case for this case because this is derivative of the function, not the. It's not the spherical harmonic. So this makes the work a little bit complicated because this orthogonality property is valid for this case, not for this case. So what can we do with it? So I have explained that you cannot use this equation for doing the determining the spherical harmonic coefficient of the psi. So instead of that, we do it in another way after this experiment. So now I want to define a mathematical model that you can determine a spherical you can determine the equation of what is called, oh my God, what's the word? The QC, the QC, deflection of vertical from the end. Simply, instead, you can, if you put for n, and m is 1 over 4 pi integral n theta prime lambda prime, and not it, y and m, then you insert this back inside the formula, you can find an equation like this. I will write the whole equation at once. It will be 1 over 4 pi integral of then 2 to infinity, and it will be yes, m, that will be y and m over theta multiplied by y and m, to the y and m theta prime. Then it will be m prime or n theta prime. This. What is this one? If I do not take the derivative, then it will be addition theorem. Addition theorem. If we do not consider this one, then it will be 2n plus 1 pn cosinus psi. So now we have this derivative. If I take the derivative of this, its derivative comes and sits here. Therefore, I can write this addition theorem like that. This is a derivative of the addition theorem. In this case, I can write sigma is 1 over 4 pi integral of infinity 2n plus 1 times cosine theta and theta prime lambda prime d sigma. This is an integral equation connecting the gravity the geoid height to component in the north-south component of the deflection of vertical. So similarly, you can determine eta the same fashion. The same kernel, not the same, but with a little bit different. Then here is, oh my God, sine theta lambda n prime or n theta prime lambda prime d sigma. So you have n here, and you will get the deflection of vertical on the left hand side. Simply, you can adjust this formula like that to get, for example, if you have gravity anomaly here, for example, if you have gravity anomaly here, it will not be difficult that you will get this formula, and you will have R here. And for the gravity disturbance, I can write similarly with another color. So if it is delta G, this will be n plus 1 instead here, and R will be R in both cases. So you see that If I have a gravity anomaly, gravity disturbance, the geoid, I can determine the components of the deflection of vertical using the formula, simply. But the problem of determining the geoid, gravity anomaly, and gravity disturbance from deflection of vertical is an inverse problem. And we need to use vector spherical harmonics.